Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about car alternators. So let's dive right into it, into a generator that all of you have almost. Basically, cars have a lot of electrical subsystems and many of these systems are what we call critical, meaning they have to work. It's not optional, they have to be there. Now, the biggest requirement of alternators are basically to charge the battery. Now you may be like, why? Well, if you don't charge the battery, how the heck you gonna start your engine next time? So that is one critical aspect. And spark plugs, there are alternate ways of firing spark plugs without touching the battery. That's how old cars used to work. But you have to have, if you want electrical start, you have to have this puppy, starter motor draws huge amount of power. So only way to fulfill this puppy is to have a battery, and battery is not an energy source, it's an energy carrier, so you have to pump energy into it in order to extract it. So that's why we have to have a generator in our car. And there are other things that are critical. For example, headlights are huge power consumer. We don't think about it, but they are generally 100 to 200 watts of power consumption on an average car. So that's a important thing. And even in daytimes you have to worry about brake lights. One brake light is not an issue, but you have multiple of them, so you can be easily looking at 5 or 10 watts of power draw. Now how many times you apply brakes? So that's also another power. In case of rain, in India it rains for almost a month, so wipers are also another thing. And we are adding a lot more of electrical systems. For example, electrical seat heatings, infotainment systems, very complicated music system, powerful music systems, electrical steering pumps, basically, which helps us power steer utilizing electrical systems rather than hydraulic system. And then we have anti-lock braking system, which also requires another electrical pump. So reality is we are adding more and more and more and more. So we must have a way to provide power on top of that, because engine has such a large RPM range. Whenever you talk about generator set, which we have as a backup generators, they have fixed RPM like around 1500 RPM or whatever the design intent would be. It would be more or less that. But when you're talking about car, the RPMs have very huge range. For example, you can have a car that starts at as low as 200 or 500 RPM, and then idles at around 1500. Let's just go with that. And then it goes, the moment you press accelerator, it can go as high as 10,000. Now think of it this way: if you have a generator directly connected to that kind of RPM, you must have very good control. Otherwise, you will have, hey, at idling, my battery is charging, everything is awesome, 14 volt awesome. You press the accelerator, your battery went boom, simply because you started to pump 100 volts into it. So you have to understand, we must have good control on that. So the design that allows us to achieve all the stated goal is basically three-phase synchronous generator. Now three-phase, you will like, why the heck we want to have three-phase in a basically DC system? Well, reality is almost all generator that moves in order to create electricity generally will create AC, even DC generator. The only way we can bypass that issue is that we have commutators that break the flow of electrons. So if you look into through an oscilloscope, you'll say tuk, 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 tuk. It's never going down, it's just like tuk, 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 tuk. But if you had slip rings, basically rings that are continuously connected, you will always find AC waves. Like, you cannot bypass this. If you are using motion, sooner or later you will get AC. So we use three-phase AC synchronous generator. Synchronous simply meaning the RPM is locked to the frequency. So if you press your accelerator, RPM of the generator could be sometimes even geared. So it could be in a scenario where it's like 1 RPM of the engine is 3 RPM in the generator. You can have like 1000 RPM or 2000 RPM or 10,000 RPM. The frequency could go YOLO high, as in like 200 hertz to 300 hertz or even more. So that's a real thing. And now three-phase synchronous generator, we utilize that simply because it's an AC system. Three-phase allows us to utilize the radius very efficiently, and it's what we call rotating field type alternator. What does that mean? That simply means the stator is what's producing the bulk of the energy, and you are extracting energy directly from the stator, not from the rotor. Rotor does have connection. Rotor does have what we call field coils, electromagnet basically, but it's the main controlling algorithm for you. Basically, this is the what you control in order to control the output of it. So this generator can, like, if you do not tamper with it, if you put as much voltage as you can put into the main rotating hardware, basically the field coil. A field coil is, let's say, energized to the maximum capacity. Directly you connected it to battery and you're letting it spin as high as possible. This puppy will end up producing 50 watts, 50 volts, 60 volts, 70 volts, or even higher. So you control this point. So you have stator, that is your main energy output. Then you have field type. Now field type goes through what we call voltage regulator. So this puppy will notice everything. It's like, is the battery good? If it detects battery is at 14 volts, it's like, okay, awesome, I'm not gonna pump much energy into it, barely, like, 1% energy, or basically a PWM, pulse width modulation, is used to control this puppy. So it's gonna send barely enough to just, like, keep it running, keep things going. And then it's like detects it, like you started your headlights, you started to blast music, and everything is all air conditions are all. If it's an electrical driven one, then you are noticing a very huge voltage sag. In that scenario, it will be like, hey, voltage drop to 12 volts. It's gonna open the PWM signal to, let's say, 50% duty cycle, and then the electromagnet that's here will act as a much bigger electromagnet, much more powerful. Then the stator will start to produce more power. Consequence, it will start to draw more energy from your car engine, but that's the intent of it. You don't want to think about it, you just want to, like, press accelerator if you need to. So this puppy will directly start to produce more energy, and that's how you control the voltage throughout the large RPM. So it will always produce around 14 volts or 15 if maximum. Like, if you there are systems that allow you to find over tune a bit much, so you have a voltage drop. If you have a very thick fat cable going through a long distance, it will have a voltage drop. So sometimes people are like, hey, let's just make it 50, so everything is awesome with that, but it will never exceed that. It's like, that's the whole point of having this voltage regulator and slip rings that energizes the electromagnet here. This is your control point. That's how you control the voltage output. Now, because it's a DC generator, like it's acting as a DC generator, you don't have to worry about frequency, because this produces a 3-phase AC. It goes into bridge rectifier. So this is what things you see in the behind of every alternator. That's what they are. They are bridge rectifiers. So they take 3-phase AC and they make into smooth DC. So, and at high frequency, making DC into smooth, it's like done by default. So if you are at 100 hertz, 200 hertz, 300 hertz, this will be like absolutely smooth. You will need very high quality oscilloscope to look into, like, finding that dips. So that's how this generator works. That's the main design. It's a 3-phase synchronous system with rotating field type. So field only receives positive and negative, and that acts as a control mechanism where you can control the output. This is literally how power plants work. And there is a feedback system for voltage control, so you do not have a scenario where you overcook your battery. 3-phase bridge rectifier is utilized for making into DC. Now you will always find something odd in this system. It's claw pole rotor. Now why the heck it has such a weird looking shape? Because most people are familiar with this sort of system, which we generally classify as salient pole rotor. So for example, if this is the axle, you will have one electromagnet here, one here, one here, one here. But why the heck this has something like this, where it's like coils are like this? So you may be like, okay, if the coils are coaxial, it simply means it will create north and south. North is would be here, south would be here. You don't want that. You want north here, south here, north here, south here. But you're not having that. So that's the whole point. This is what we call a London generator. So the whole design principle of this, it creates trapezoidal waveform, because, like, if you look at it, it looks like a trapezoid. So if you go send this output of the stator into an oscilloscope, you will find it's trapezoidal. It's not sine wave. Now of course it's still AC, but it's not sine wave. The reason this was selected is simply because it translates to DC very efficiently, because you will notice that top does not have a smooth peak. It's flat. It's like top is almost chopped up. So if you do not do anything, if you just, like, do not have very high frequency, especially like in engine idle, these things will line up to a point where it's like, yeah, it's just a DC system, because it inherently is far more efficient at converting into from AC to DC for bridge rectifiers. That's why this pole is selected. On top of that, there is another benefit. It's easy to manufacture. For example, all you have to do is take a basically system, Mendel, and then just spool coil around it. Super easy, super cheap. And then you have basically forge that forges this claw system. So that's the whole point of this. That claw allows you to pinch the magnetic field. Magnetic field does not like to travel through air. They like to travel through something that is far more magnetically conductive. Again, metal. Now this metal allows it to be pinched in such a way that there's like, hey, North Pole, can you focus here, focus here, focus here, and here it will be low focus. Here is South Pole, can you focus, more focus. That's the whole point. This claw is focusing that. So one side is becoming north, one side is becoming south. However, because the claws are offset, it acts like this part is north, this part is south, this part is north, this part is south. That's the whole point of it. That's why the claw is created. Again, you will never use this for basically running your power plants or things of that nature, because again, the waveform is not suited for normal AC consumption. However, if all you have to do is send it to bridge rectifier, like that's the first thing you're gonna do, send it to a bridge rectifier. This design is awesome, and it also has another advantage, that is very power dense, meaning you can find basically alternators that are this big, and they are around 1 kilowatt, 2 kilowatts, or sometimes even 5 kilowatts. So you will have very high power density on this puppy. So that's the amazing design of this. It's super cheap to make, and just utilizing fancy metallurgy, you can create a scenario where you do not have to have fancy coilings. Now, consequence, it does create trapezoidal wave, which you do desire for DC, but you can never use this for AC systems. It will cook your electronics. So that's why we utilize claw pole rotors. I provided the video down below where a person does the, basically waveform analysis directly. So that's the whole point. It allows it to be mass produced easily rather than salient port system. Now there are some problems with this puppy. Primary problem is no generator in this world. Like if you go to any engineer, it's like, hey, can you design a generator? It's like, awesome, we got this. The moment you say, I want a generator that works at flexible RPM, they're like, dude, we can't help you. No generator likes changing RPM. Now, for example, same design, basically three-phase system that is utilizing the rotating field type is utilizing power plant. Now these puppies go up to 98% efficiency. Same design, exact same principle of operation rather than the core. Core is a bit different, but same thing. How the heck this puppy is at 98% efficient? Well, reality is it's cooled very well. So core is cooled by hydrogen. You will notice the turbine. Yeah, that's for circulating hydrogen. Inside that, hydrogen is very good at conducting heat. So then you have radiators inside the rotor unit, and rotor unit I'm saying like the casing. Inside that casing radiators cool it. So hydrogen is basically acting as a conductor medium. You have slip rings. Now because the RPM is fixed, slip rings is fine tuned, like it's perfectly grounded, perfectly calibrated, so it has very fixed amount of friction. It will never go up nor go down. And then you have rotors, basically stator. Now stator, because it's handling, let's say 600 megawatts of power, it has literal water cooling running through every single coil. So that's how they make sure this puppy at 98%. In your car, it's really not ideal scenario. For example, your car is in a heated place. Inherently remove its own heat generation. If you run your car even for, let's say, 15-20 minutes, you will notice that engine bay starts to heat up. Imagine what will happen if you are driving it for like 2 hours or 3 hours. This chamber could easily reach 70 or 80 or sometimes even 100 plus degrees Celsius. So inherently the system is in a place which it does not like. On top of that, idling efficiency is kind of higher. So you are talking about 70 to 80% efficient, meaning if it's taking 10 horsepower from your engine, it's giving you 10 horsepower electrically. Horsepower is just 700 watts or something like that. So let's say it takes 10 kilowatts from mechanical torque, it gives you around 70% or 7 kilowatts of electrical energy. That's good. But the moment you start to drive the car in the highway, the moment you start to go higher gear, higher RPMs, it will drop to 50% because it's controlling the field system. And that's the biggest issue with this. Now you may be like, what's the big deal here? Well, again, you are talking about kilowatts of power. Your engine is overproducing by a lot. If it was 98%, that means, let's say if your electrical load is 2 kilowatt and this puppy is almost 98%, you will be producing, your engine will be producing 2.1 kilowatt to provide that. Awesome. Right now, it's like it has to produce 4.5 in order to provide 2 kilowatts of electrical energy. So that's the whole point. And reality, it translates to end up like actual car mileage is bad. Like inherently, if you can have a big battery, you will literally find that you can have a bigger battery, drive everything, like again only for a limited time period. You can do this experiment. You will find that your car gives you better mileage if you are running on battery directly rather than an alternator, because alternator is so goddamn inefficient. So that's the problem. That inefficiency directly translates to higher fuel consumption, and we are adding more and more and more electronics things in our reality. So it's like, this puppy is like, dude, I can do it. I can give you as much power as you want, but do not expect efficiency from me. So you will always find this sort of power curves where it's like 1000 RPM, it's like barely produces. The moment 2000, yeah, it's good, it's very good, like 2000, very good. The moment you start to go 4000 RPM, 5000, it's like, yeah, it barely does anything. Point of diminishing return. So that's the problem with these things. They work, they are very efficient, they are cheap, they are mass producible, but they are not efficient enough for our modern use, where we want to reduce every single kilogram of carbon dioxide that we can, and this puppy alone is wasting it. So that's why, even though the design is based on something awesome, reality, the actual execution is not awesome. So what we can expect in the future? Well, reality is people are learning that same way we went from 6-volt system in electrical cars, as in like electrical subsystems of the car, we went from 6 volt to 12 volt. Now we are going to go to 48 volt. Now you may be like, okay, why exactly 48? If you are going up, why don't go to ludicrously high voltage? Let's say, for example, 50 volts, 60 volts, or 100 volts. Well, the moment you cross 50 volt, everywhere it reaches a point where it's like shock hazard, meaning if you touch the terminals of the battery, you will be electrocuted. And when you're talking about DC does not have zero voltage crossing, so you cannot even pull your hands away. So inherently it's very dangerous. So you always want to have the voltage to be as low as possible. for safety reasons. So 48 is a good compromise, meaning you can touch it, will not get electrocuted, but this is 4 times higher than 12 volt. That directly translates to you having 4 times less ampere draw. So you can have same cable harness and you can send more 4 times the power, or you can half your cable harness weight, basically gauge of the cables, and still send double the power. So fundamentally everybody wins if we go to 48 volt system, and we are letting go of electromagnets and we are utilizing magnets, neodymium magnets. Now we're like, why the heck you want to do that? Don't you lose control of doing it? Well, yes, that's the consequence, but you will look into Mercedes and Toyota and all that. They are trying to go to that direction. Why? Well, they are utilizing power electronics, meaning the inverter system, basically that's going to take the AC coming from the generator and make into a stable DC. That has improved a lot because of solar farm developments and basically wind farm development. All of them require huge inverters. So because of that development, we have technology to have a system where generator can go from, at idle it's barely producing, let's say 50 watts, 50 volts, and at ludicrously high RPM, basically engine max RPM, it could be producing 200 volts. The inverter unit can handle it. It's like, I got this, I do not have to worry about, because there is no control here. You can't reduce the magnetic field. Their field is not controlled. It's self-excited field, meaning the permanent magnet, so you can't control it. So you can directly go send it to all the energy to inverter. Inverter is like, I got this, I'm only gonna give you 48 volts, don't worry about it. So that's awesome. And there is another improvement that every car manufacturer is trying to do, is basically direct drive as many auxiliary system as possible, meaning have this generator. Now again, if you are talking about something that is directly connected with a power inverter, you're talking a lot more power. So you will go from barely, let's say 1 kilowatt energy system to 3 or 5 or even 10 kilowatt system. So what you're gonna do with that much power? Well, you're gonna remove as many timing belts, pulleys and all that as possible, because there are many things that are directly connected to engine crankshaft. For example, coolant pump, hydraulic steering pump, meaning power steering and all that jazz. Then you can have other things also. So the more things you remove, especially air condition barely turns on, but like most of the time it's still spinning because of a disconnecting clutch, but that is a parasitic loss. Why the heck you are spinning that mass if you don't need to? They are like, okay, disconnect that. So everything will be electrically driven as far as possible, and all you're gonna do is directly drive them from this puppy. So meaning when it goes to off state, this will have a lower resistance, meaning the engine will spin idle much more efficiently. So all the calculation is that doing a direct drive system and going to 48 volt system, you're talking about 10 to 25% fuel savings. So that is a very big deal. Think of it this way, like you can run your AC and your car bill does not go YOLO, your fuel consumption YOLO. That does not happen, because this is far more efficient use of that. Your car is also lighter simply because it does not need to use as thick of a cable as possible. So that also translates into actual weight saving. That translates to actual fuel saving. So all things considered, this is one of the ways that we're gonna utilize basically better car engines in the future, and we're gonna reduce the number of parasitic losses, basically coolant pump, steering pumps, air condition. These are generally the big ones. If you can remove all of that, so coolant pump will only come on, it's like, hey, engine is hot, okay, let me cool it down. If engine is cool, it's like, dude, what the hell? Or heck, sometimes you don't even want to cool it, especially in cold climates. If it's very cold, you really don't want to overcool it. That will put too much stress on the metal. So if it's directly connected, you can't do much. But if it's electrically connected, you're like, whoa, relax, let the engine bay warm up a bit, then we're gonna circulate something. So that's why this is the future, where we're gonna have 48 volt system that will reduce the ampere loss, and then directly try to drive as many things as possible electrically rather than timing belts. So this is what we can see in the future. That will help us to reduce the carbon footprint of every single internal combustion car. What about electrical car? That will still take at least 30 years before it becomes common. So this was my presentation on car alternators. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.